Hello, today I'm going to explain to you how you can derive the work-energy relationship with calculus. I'm going to derive this today because a lot of people just use this formula without actually knowing where it comes from. And yeah, we use it all the time in mechanics, physics, but where does it actually come from? That's what I'm going to answer today. Okay, so the first place we're going to look at the acceleration, and see what we can get from that when we use the chain rule along with it. Okay, so acceleration, we know that it's equal to the change of velocity with respect to time. Okay, so if we use the chain rule on this, we can kind of, let's say, split it apart into the derivative of velocity with respect to displacement multiplied by the derivative of displacement with respect to time. This is useful because we know that the derivative of displacement with respect to time is also velocity. Okay, so we can say that acceleration is equal to the velocity multiplied by how that velocity changes with displacement. Okay, so you can see how from doing this we've essentially just got rid of the time variable. Okay, anyway, so now we've essentially got a differential equation which we need to solve. Okay, so we're going to times up by the dx. I'm not even going to get into that, but yeah, we're basically going to integrate both sides. Okay, so left side, a is essentially a constant, so that's just going to go to ax. Right side, v is what we're integrating with respect to, so that's not a constant, so it's going to be v squared over 2, and then don't forget the plus c. Okay, how are we going to find that constant of integration? Let's have a look. So we need some initial conditions. Okay, so what we're going to use is that at displacement equals 0, the velocity equals some initial velocity. Okay, so if we just plug this in, we get a times 0 equals v naught squared over 2 plus c. Okay, a times 0 must be 0. We know anything times 0 is just 0. Okay, if we rearrange a little bit here, you get that c equals negative v naught squared over 2. Okay, now if we just plug that back into our original expression, then we get ax equals v squared over 2 minus v naught squared over 2, and then we're going to rearrange that a little bit, and then that should be very familiar to you. V squared equals v naught squared plus 2ax, or you might have seen this before as v squared equals u squared plus 2as. Okay, same thing. Yeah. Now, this is one of our kinematic equations, and now we're going to start deriving the work-energy relationship. Okay, this has basically all been preliminary stuff, but I just wanted to show it from first principles. Okay, so now we're going to start from F equals ma, which basically the most important thing in physics. Okay, Newton's second law. Force equals mass times acceleration. Okay, acceleration is what we're interested in because that's the only thing that appeared in our equation before. Okay, so if we just rearrange here, divide both sides by m, we get a equals f over m. Okay, so our expression, we're going to plug in f over m where a is. Okay, we're going to substitute that in. Okay, multiply everything through by m, and we get mv squared equals mv naught squared plus 2fx. Hopefully now you can see kind of where kinetic energy is coming from when you start seeing mv squares getting thrown about. Okay, now we're going to take that mv naught squared onto the other side, and then we're going to divide by 2. Here we are, fx equals half mv squared minus half mv naught squared. Okay, that is our work energy principle. Okay, fx is what we define to be work. Half mv squared is going to be our final kinetic energy, and then half mv naught squared is going to be our initial kinetic energy. Okay, so that overall is going to be the change in kinetic energy. Okay, and that's where we get W equals delta EK from. That's it. Therefore, all the work done onto a system is equal to the change in kinetic energy. Right, so that's the video done. We have proved everything we were aiming to prove, and if you could like and subscribe, that would be great, as I'm trying to grow the channel. See you in the next one.